Hello everyone. Now we are moving to new chapters. So we finished the polar coordinates, and the parametric equations. Now we have the vectors. Okay. Vectors. We start with the vectors in two-dimension vectors. Okay. So what is vectors? Okay. Vectors is it has. So let me get the magnitude or value, and it also has a direction. If it is only having a value or magnitude, we call it scalar. Okay? So vector is a special terms that describe something that has value, but it has also directions. Okay? For example, we take this, let's say it's point A, okay, and then to point B. So it's something moving from A to B, and we could call this vector u. Let's say this is a vector u, as we can also write this as a, b, and then get an arrow on top of that a, b. Okay, and we could also think in, if we have 3 points, let's say a, b, and c, we could describe this. For example, we move to a from a to b. I think we need to make sure. Okay, we move from A to B, and that's our vector. And then we also move from B to C. And that's our vector. Okay. And we could say this is AB, and this is BC. Now we could also get the AC, like this one. Okay. So we could say that this is also a vector, okay, AC. And in vectors, because we start like from A, we move to B, we move to C. So we could say that factor AC, we could describe this AC as factor AB to BC. Okay, it's also can be written as AC factor is AB plus BC. Okay. How to obviously observe or confirm that this is true? We could see from the factors here from A, B, and BC. We could see this start A, ending with C. Okay, and it's AC. Okay, it's the easiest way to see how it looks like. Okay, and whenever we have a vector, for example, you have two factors like this, okay, and we say that we have another one that is getting from there. Okay, let's say this is u, this is v, this is u plus v. Okay, and this is also true if we have the same u and v. Let's say this is u, but now v is here. Okay, we could move out this v. We could move out this part, this vector v. We can move out and make it around here. And then we could describe that this part here is our resultant, or our addition of that factors. So this is we called u plus v, the same. Okay, so you could also can move the vectors as long as it's not changing its direction. Okay, as long as it stays the same direction, we can move in every space we want. Okay, and we could also can multiply factor can be multiplied with scalar. For example, let's say we start from this magnitude and directions. which is, let's say we have u. We could multiply with maybe half, and then we say this is half u. We could maybe multiply with 2 or twice of the length, and we say this is 2u. And we could also multiply with a negative. So when we have this part here, but the direction is the opposite, so we say that this is negative u. Okay, and the same thing, we multiply with maybe 1/3. We say this is 1/3 or negative 1/3 u. Okay. So if we take, let me copy this and see if we have the negative part of it. So we can also have, okay, if we are multiplying with the negative u, the negative u will be, let me draw in here. This is just to note that this will be the negative u if we multiply with negative. Let's say this is negative u. Then this part here, let me goes here, and let me take it with another color. So this part here is u, or v minus u, right? Or if you want to make it more clear, this is v. This is the negative u, so this will be v minus u. Okay. Okay, we continue the vectors. Okay, so we define the vectors already, and we can form a component that forming a vector. So let me just give you the picture. Okay. Let's say we have a vector v. We have a vector v that is from point P to point Q. And if we imagine that this vector is in two-dimensional space, in y-axis and x-axis, then we could describe the vectors in terms of x and y. So we could take this, okay. So vector v is the component x and component y. So vector v represent in the plane with initial point P. And terminal point Q. Okay, so, and you need to focus on this brackets. This brackets is when we are dealing with the vectors. So as in general, the vectors we could describe in two dimensions. We can write this as this. Okay. So that's a component form of a vector. So we can have an x, y component. Okay. And then you could take the component to calculate the magnitude of the vector. So the magnitude. So if we have this vector the component of x is a1, component of y is a2, then the magnitude value of the vector v is equal square root of a1 squared plus a2 squared. This came from the Pythagorean, okay, the Pythagorean theorem. Okay, so this will be the magnitude of vector v. So we usually write down the magnitude as with the similar to absolute value, okay, in a vector. And then because of this component also, we could take the algebraic operations in vector. So we have, if we have u and v, then we want to plus these two vectors, then we need to plus the each component in each form of components. Okay. If we need to multiply with a constant, then we need to multiply all with those constants. C is on the real number constant. Okay. And then there are some property of the vectors that perhaps I just put here and you can take a look. Not this. This is algebraic. Okay. So we could add, and you can. It will be the same whenever you start. And then you can multiply by scalar, and then you can multiply by 0, and then you could also look at the length of this vector. We could also describe as it is. Okay. And another component that is important is the unit vector. Okay. Unit vector, okay, is having this. Okay. So we say unit vector is when the component of the vector each has one unit. We call them with this I and j. So vector of length 1 is unit vector. So we say that the I is equal 1, 0, and j is 0, 1. Or you could have arrow in top of that, but I think it's still okay. Usually I'm writing the arrow because I want to make this distinction with other variable. In your textbook, if you have your textbook, you don't have the arrow, but you have the variable or the symbols. The letter is already in bold, so it's already distinct. Okay. So if we write in terms of I and j, we could write the vector v is equal okay. We write in terms I, j like that. So unit vector, and then the another part is the horizontal and vertical component. And I think this is supposed to be easy to follow. So we have a magnitude value of vector, which is the vector v. So let v be a vector with magnitude and direction, or angle direction is theta. Then v where a1 is, we could describe in this sine and cosine analysis. Okay, and then we can express v, the vector v, like that. Okay, so we can express the vectors into component of sine and cosine, that is the component of the vertical and horizontal. Okay, so this is going to be horizontal and vertical component of a vector. Okay, now the next sections will be about the dot product. Okay, let me define the dot product. Okay, let me define the precise definition. Okay, if we take the two vectors u and v, and they have their components as in a and b, a1, a2, b1, b2, okay, and then the dot product u dot v is equal to a1, b1 plus a2, b2. So the result of the dot product, this will be a scalar value. Okay. This will be a scalar. So it's not a vector, but rather is a scalar. It's a real number, right? Okay. Some of the property of this dot product that we have is here. So we could say that if you take u dot v, it's this equal with v dot u. Okay, because at the end you just need to add the multiplications, so it should be the same thing. And if you have a constant, you can factor out the constant, and then you can move to the other vectors as well, because they have the same or similar property. And then u plus v dot w, we could separate them, becomes u dot w plus v dot w. And then the last thing is, if you take the dot for the same vectors, then you will have the magnitude value, and then you can square it. Okay. It's as simple as, if we take the u dot u, we could have a1 plus a2, or a1 squared plus a2 squared, which we know that the square root of this is the magnitude of value. So this is actually magnitude of value of the square, and then squared. Yeah. All right. Now, if we let the let's say we have this u and v in terms of the two-dimension space in x-axis, y-axis. Okay, we could describe, let's say the vector u is from origin to a, vector v is from origin to b, and we have the u minus v. Okay, so remember that this is taken by u, and then we could take the resultant as in, so if you don't remember, we can move out the, let's say this is the v, but let's say we have taken the opposite v, that is minus v, and a u minus v is this part here, which is the same thing as the u minus v, and then we can move out also, and then we can simply say that u minus v is this this value here, right? Okay, now from this u minus v, if we apply law of cosine, which means that we are going to include this theta, because it's in front of this factor, right? So in the law of cosine, the length of u minus v, the length means the magnitude value, is u minus v squared, right, is equal to the length of the other sides, we plus these two, and minus of this 2 uv cosine theta, right? And then this part here we could write as u, or maybe we take in the different equations that u minus v squared is, if we factor out these two, we can factor that this will be a two factors that we could say like that. Okay, and then within the property of the vectors we could transform this one by one, and we could say that this will be u dot u minus u dot v, okay, and then minus v dot u, and then plus v dot v, and then we can simply write down this as u squared minus 2 u dot v, okay, plus v squared, the magnitude value. Okay, and then we equaling this to the right hand side. So u squared minus 2 u dot v plus v squared is equal cosine theta. Okay, and then we simply solving this out, so we can cancel all this part, right? And then it's going to be minus 2 u dot v minus 2 u v cosine theta, and we can cancel this out, and we say that u dot v is equal magnitude of u, magnitude of v, and then cosine theta, and this will be the dot product theorem. So the theorem says that if the theta is the angle between two non-zero vectors u and v, then u dot v is the magnitude of u, magnitude of v, and multiply with cosine theta. Okay, and then from this theorem also we can find the angle between the two vectors. We just simply rewrite this as this. Okay. Okay, and then we could also make a conclusion of the orthogonal factors. So we know that u dot v, okay, this is the equations. So orthogonal means that the vectors, let's say this is u, this is v, this means the orthogonal. Okay? So v is orthogonal to the u. What the orthogonal means is we have this angle, which is 90 degree or pi over 2. So if we have this pi over 2, then this u dot v is equal to 0. So if u dot v is equal to 0, then two non-zero vectors u and v are perpendicular. Okay. Okay. Now the same principles. Okay. When we have this kind of two vector situations, is we will have the component, okay, the component of u along v. So which means that we know that the component, if we take the this is u, and we know that this will be a theta, then if we take the component on the sides, okay, let's say this side here, this will be u cosine theta, right? So, and we could exactly try the the dot product, that is u dot v, is u v cosine theta, right? So if we take the u along v, then we will have u cosine theta, and we need to divide this with v. Okay. And then this will result in u dot v divided by v. Okay. So component, or let me just take in the picture to make it more clear. So we could have the not this one, sorry, this one. Okay, the component of u along v. Yeah, this is v. So this component means it's just a component of u. Okay. There are another applications, which is the projections. Okay. So if we project like this, so this is the projections. So projection of u onto v. Okay. So we have a view, and then we project, and then this will be the projections. Okay. And then we could take the similar approach, and this will be the result. And then we could also conclude that if the vector is resolved to u1 and u2 becomes two vectors, and u1 is parallel to v and u2 is orthogonal to v, then we could see that this will be the projections, and the other vector is the vector minus the projections. Okay? If this is going to be having the two vectors in one vectors. Okay, so one vector becomes two vectors. Or we could think the projections is actually is the component of u along v multiply with unit vector in direction v. Okay. So the component is u dot v. So the component is u dot v over magnitude of v. The unit vector is v divided by magnitude of v. This is the unit vector, right? This is the component, okay? Okay, I hope you get the idea of, at least the basic idea on dot product. Okay, so after we finish the vectors in 2 dimensions, let's see vectors in 3 dimensions. But before we look on the vectors, we are going to describe what is three-dimensional rectangular coordinate system. Okay. So let's dive in. So 3-dimensional rectangular. So by rectangular, I hope you remember what we have in the previous chapter, which we described rectangular and polar, right? So the system consists of 3 axes rather than 2, as in 2 dimensions. So we will have the x, y, and z. So usually we take this as, so well, depends on some references, but some they are taking this as x, y, and z. Well, some maybe they switch the z and x, but I think still okay. It's still three-dimensional system. We take the middle part of those three line intersection as the origin point. So this is what we have, okay. And between these three axes, there's we call the invisible wall. So you cannot see the wall, but it's there, and we could see the wall as a plane, okay, if you would like to say that. So this will be those walls that we have. So in the three-dimensional system, we have the YZ plane, XZ plane, and XY plane. So we have like an invisible walls in between these axes. So between the Y and Z, we have this YZ plane. Between X and Z, we have XZ plane, and so on and so forth, okay? And then we could describe the points on the three dimensions as this. So when we have point, let's say in this space, and we call P, so this means that we are having A, this is x-axis, A positive, well, this is positive A, and then positive B at the y-axis. So we are kind of look this point as we move from origin, and then we move one by one. So we move A, and then B, and then C, okay? And then from here, we could also describe that if we have a line equations in three-dimensional system, for example, if we have a z equal 3 or even a y equal 5, we know that in 2 dimensions, these two equations will be just line equations, right? But in 3 dimensions, if we have this it is supposed to be line, then in three dimensions, this will become a surface. Okay? So we could draw this as this picture here. So which means that at z equal 3, so we could take that red dot point, and then we could imagine that there is something crossing this point 3. Okay, we could imagine like a paper or like a plane, okay, the plane that is cutting the point equal 3. And same thing when we have y equal 5, so we could describe this y equal 5 in y-axis at point 5, and we could see some plane that is going cut through this y equal 5, okay? And then also in the 3 dimensions, we could describe the point like this point. If we could describe point P and Q, and we try to count to measure the distance between PQ. Okay, so the distance of PQ we could describe by taking the descriptions of all x, y, z, and then we could describe the distance formula as in the 2 dimensions also. We could describe that, and then we could describe as this formula. So this formula, if you think and try to make the formula make sense, we could see that we have this x1, x2, y1, y2, z1, z2. So the difference in between all this, and then squared, and then plus of all of those results, and then square root, then it will be a distance. It's the same thing as in 2 dimensions. We are applying the Pythagorean theorem for this whole line. Okay, so if we take this as well, we could see that this, let's say A and B, okay, let's say this A and B. So A could be described from this line here. Okay, we could take this another Pythagorean and make it into A, and then B, we could see that the B is just difference in the height. Okay, the height is Z, right? Z1 and Z2. So A is described from X and Y, that is this part here, and this will be B. So that's it. We could simply just take this as our distance formula. okay? And then another thing we could also describe in terms of this sphere. Okay, we could see that we have a center, we have a point, okay, and then this is like a sphere, like a ball. And we could also describe the center using the formulation for sphere and describing as this formula. Okay. And we could describe this using the distance formula also. So we could describe using the, I think it's too small, let me make it bigger. So we could describe the distance of point P to C, and then squared is equal of all this. Okay. Well, it's the same thing as the distance formula as previously mentioned here, right? So we could take this x minus h, y minus k, z minus l, okay, and then all take each of them squared and then plus. Okay, so that's why we have this formulation. So the distance is our radius actually, right? And if we are given examples like x squared plus y squared plus z squared plus 4x minus 6y plus 2z and plus 6 equals 0, we can try to make out this the standard form of sphere equations. So which means that it's going to be this, okay, this form. Okay. You need to take the complete square of the equations. Okay, I think that's the additional information for the 3-dimensional. Okay, now after we had discussion on the 3-dimension system in for vector, then we could describe vector itself in space. So this next section will be about the vector in space. Well, we could describe the vector v with the terms of a1, a2, and now we have 3 components, a3. So we could describe this in this picture here, that we have a 3D system, x, y, z axis, and we could describe v. For example, this is our v, vector v. We could describe the point being a1, a2, and a3. Okay. And then we could also describe this in a more describe. Okay, I think it's still the same as in 2 dimensions, but we need just to add one more axis, which is the z. Okay, and then the other thing is also similar, that is the magnitude value and the algebraic operations. Okay, so algebraic operations and the magnitude value of the vector v. Okay, so if v is a1, a2, a3, then the magnitude value will be the square root of the a1 squared plus a2 squared plus a3 squared. Okay, and then we can combine the vectors, because, and also if c is scalar, you can also multiply the vectors by a scalar. Okay, I think not really any complications here. Okay, other things aside from that is the unit vector. So of course, because it's 3 axis, then we have 3 unit vector, which is described by I, j, and k. So I is a unit vector for 1, 0, 0, and j is a vector of 0, 1, 0, and k is 0, 0, 1. Okay, And you can see how it's described as in each axis they have their own vector that has length 1. That's the description of unit vector. So unit vector, recall that unit vector of length 1. Okay. So that's why it's 1 unit on x, 1 unit on y, 1 unit on z. And we could describe the space, or in the coordinate in space with vectors using the unit vector as in this. So we could describe the vector v using the a1i, or you could describe v using a1i plus a2j plus a3k. So we can express the vector in terms of I, j, and k. Okay, also we could take the dot product of vectors in space. So let's say we have u is a1, a2, a3. We have b, b1, b2, b3. And the dot product u dot v is defined by a1, b1 plus a2, b2 plus a3, b3 is still the same, just adding one more components of the third axis. And still the conclusion for the dot product is the result will be a number or scalar. Okay, now if we take the angle between two vectors, and remember that we have this relations using the cosine. So if the theta is angle between u and v, so theta is angle between vector u and vector v. And then also we know that u and v perpendicular or orthogonal if vector u dot vector v is equal to 0, right? So it's also the same thing when we've done the example here. So if we take the example, let's say we have a vector u, 2i plus 2j minus k, and a vector v. And we would like to know whether these two are perpendicular. So the first thing, we need to find the dot product. So take the u dot v. So 2 multiplied by 5 plus 2 multiplied by negative 4 plus 2 multiplied by negative 1, right? So we have 10 minus 8 minus 2, which is 0. So we know that because this is 0, so due to u dot v is 0, then u is orthogonal, or u and v. R orthogonal, right? Okay, another one that is, I think, because in space we can have some directions, and the angle can be also rotate, right? We could have in 2 dimensions the angle will be in the plane, while in the third dimension the angle will be in the space, right? So we could see that when we moves the directions, the angle also moves. So if we take our times to look at this, so the vector v can be described with these 3 special angles. So the angle from y-axis, which we call the beta, or we could start from alpha. So the angle between x-axis and v is alpha, and the angle between the y-axis and v, beta, and also the third one, the angle between the z-axis and v, which is gamma. So all this alpha, beta, and gamma, we call them as direction angles. That is the angles between the vector with the axis, okay? Okay. And then if we take the cosine alpha, and we know the formula, so this will be v dot, and let's say we have a unit vector. In terms of this axis, each one has the unit vector I, j, k, right? So let's use that. So I, j, and k. So let's use that as our vector here. So v dot I and this is actually v dot I is a1. Okay, maybe let me write here. V is a1, a2, and a3. This is x-axis, y-axis, z-axis. And we also have cosine beta is v dot j it's a1 over v. This is a2 over v. And then cosine gamma this is a3 over v. Okay. So the direction of cosine, if the magnitude value is 1, then the direction of cosine, this is direction of cosine. So direction of cosines of v are simply just the components of v. Okay. And then one of the special property, or we could write this in more general applications. We could rewrite the cosine here within these terms. And one of the property is when we have cosine squared alpha plus cosine squared beta plus cosine squared gamma, they are equal 1. I think that is the vectors in 3 dimensions. Okay, the next sections we are going to have the description on the cross product. Okay, so the cross product So let me give you some idea on cross product. Okay, so let's say we have our vectors. Let's say vectors u and vectors v. Okay, and then sometimes we need to find. Okay, sometimes we often need to find another vectors. Let's say w that is perpendicular to u and v. Now, if we write the w as another c, let's say c, then because of the perpendicular, then the dot product of u dot w will be equal to 0, and v dot w also 0. Now we could rewrite this in more details, like a1c1 plus a2c2 plus a3c3 is 0, and also b1c1 plus b2c2 plus b3c3, they are also 0. And if we try to solve this, okay, and we could see that one of the solution of the system of equation is the vector w is a2b3 minus a3b2 a3b1 minus a1b3 and then a1b2 minus a2b1. Okay. This vector, this vector w, this is what we call the cross product of u and v. Okay, and we usually denote this with these terms. So the cross product, let me give you the definitions. So if u and v are three-dimensional vectors, then the cross product u and v is the vector. So we define the cross as, we say this part here as u cross v. Okay, u cross v. Okay. So to help us remember what this actually means in another terms, let's imagine that we have a two dimensions. Okay. If we have two dimensions, the determinant of order 2, if you happen to learn before, especially the matrix, we will learn later on the matrix, but let me just rephrase this as a determinant, which described as AD minus BC. Okay. So AD minus BC, that's the determinant of order 2. And if we have the determinant of order 3, let me write in more clear space. So we will have A1, E2, A3, B1, B2, B3, C1, C2, C3, and then this is it. Okay. So the determinant of order 3 is A1. This is B2, B3, C2, C3. Okay, let me tell you later how to get this pattern to knock off this uh, solutions. It's actually pretty easy to look at, but let me just write first. Okay. Now, this part here, the order tree, okay, let's say the order tree, we need to describe and take some row, okay. For example, row 1, let's take row 1, and we will denote A1, A2, and A3, okay. Let's start from A1. If we take A1, then we are going to cover this part, and you will see that we have this square, okay. And this is how we process. So A1 will multiply the determinant of this square, the red square here, B2, B3, C2, C3, okay? And then do the same thing for A2. So A2, so let's cover the whole row and column, and we are left with B1, B3, C1, C3. That is this square. Okay, so determinant of this, but we need to multiply with negative. Okay. Later when we learn about matrix, I will tell you why we need to have this negative. Okay. And A3 also the same. So we are covering this part, row, one column. So this will be our square. This is our square. So if we apply the determinant calculations, then this will be and this will be the result, right? Now, to help us to compute the cross product, let the A1, A2, and A3 becomes I, J, and K. Okay. Now, if with this A, J, and K, then we could write I, J, K, A1, A2, A3, B1, B2, B3. Okay, so this will be A2, B3 minus A3, B2, I minus A1, B3 minus A3, B1, J, and then plus A1, B2 minus A2, B1, and then K. Okay. Now actually, just some notes for the determinant of the matrix. Well, this is true for A1, A2, A3, but it's also true if you take the second row. So this is the first row, right? So let me write with the green color. So this is the first row. This is the second row. This is the third row. For example, if we want to take the third row, then we need to write B1, but we need to multiply with negative, and then multiply with A2, A3, C2, C3, and then plus B2, A1, A3, C1, C3, and then minus B3, A1, A2, C1, C2. Okay, And you could also take the third row, but the third row will be plus minus plus. Okay? So it's actually a pattern that we call within the matrix. It's called the covector, but we'll learn later in more details. But we are going to multiply with positive, negative, positive, negative, positive, negative, positive, negative, positive, like that. Okay, but for now, for the cross product, we just need to write the top equations, okay, as ijk. And you'll see that this is the same thing as what we did when we look at the definitions, okay, in this definition here, the cross product, right, the W. So this will be the cross product, the process, okay. Well, there are another way to get the cross product, and I think this will be very, very helpful. My way to work this out, okay, is let me write in green. So I, J, K, this is A1, B1, A2, B2, A3, B3, and then I will add more columns I and J. So rewrite all the first two rows at the first two columns. So A1, B1, A2, B2. Okay. The next thing is we are going to multiply, cross multiply this part. Okay. So let's cross multiply that part. So this will be A2B3I, okay, and then plus A3B1J, and then plus A1B2K. And then we cross multiply again within this. But now we are going to minus. Okay. So minus all those blue multiplications. So minus B1A2K plus A3B2I. So let me, maybe this will be A first. Maybe it's better this way. And then plus A1B3J. Okay. And then try to look at, this will be A2B3 minus A3B2I. And then plus A3B1 minus, right, minus A1B3J, and then plus A1B2 minus A2B1K. The same thing, right? Same thing. Same. Slightly different on the middle, but it's actually the same. This is just plus here. This is negative. Okay, but the result is the same, right? If you change the signs, it will be the same. Okay. Usually, I'm doing this for cross product. It's up to you. You can just take the original one like this, or taking my steps. Right. Okay, so the cross product says that the vector U cross V is orthogonal to both U and V. Okay, this is the cross product theorem. Okay. We could see that this theorem is true if we can prove that the cross product of U cross V, when we dot with U, will be the same, or 0 in our case. Now if we dot product with U, then we are going to write exactly these notations here. Okay, so if U is taking the A1, A2, and A3, so we are going to have, this will be A2, A3, B2, B3, but this will be multiplied with A1 because it's going to dot with U. Okay. U is A1, A2, A3. And this will be A1, A3, B1, B3. This is A2 and plus. So this will be A1, A2, B3 minus A3, B2 minus A2, A1, B3 minus A3, B1 plus A3, A2, B1 minus A1, B2. Okay. And we are going to look at what we have. Okay. So let's just multiply one by one and see how it goes. I will consistently write the less number on the left and the greater number on the right for the order, right? So A2, A3, and AB will be, so A will be the left, B will be the right. And you'll see that this part is this, with this part is canceling. Right, and then A2 plus A2 minus minus so it's supposed to be, let me check. Oh, it's supposed to be negative 2A1, A3, B2 plus 2A2, A3, B1. Is that it? Oh, wait. I almost getting wrong here. Sorry for taking long, but I think I make a mistake. This is not A2, this is supposed to be A1, B2 and A2, B1. Okay, so the whole thing here is wrong. That's why I never got the correct conclusions. Okay, now we can cancel this out and cancel this out, and all will be equal to 0. And we prove that this the cross product is orthogonal to vector u and v. Okay. Okay, sorry for taking that long. Okay, another representations that usually we use, I think in high school you already learned of that, is we are going to using the right hand rules. So we could think that this is a vector, this is a vector, okay, and the result of the u cross v is going to be your thumbs. Okay, you can use your right hand, and the length of the cross product if we have the angle between u and v, then the magnitude of u cross v is equal to magnitude of u, magnitude of v, and sine theta. And the vectors will be a parallel if the cross product is 0. Okay, so we can say they are parallel. Now we could take the the definition of cross product, okay, and length. So we take u cross v, and then we square this. Okay, so the whole thing in the definitions, where's my definition? This cross product here. I will square all this. Okay, I will square. So this will be a2b3 minus a3b2, and then squared, plus a1b3 minus a3b1 squared, and plus a1b2 minus a2b1 squared. And then within certain formulations, if you remember taking the factorizations of a squared plus b squared or a squared minus b squared, we could take the a1 squared plus a2 squared plus a3 squared, and then taking out b1, b2 all within the squared form, and then minus the a1 b1 plus a2 b2 plus a3 b3. Well, it's a little bit tough factorization, but let me just show you that this part is u squared, the magnitude squared, and then the v squared, the magnitude v squared, and then minus, this is the u dot v. So that part is u dot v. So u dot v squared. And we still write this as it is, and we change the u dot v becomes the magnitude. Okay, and then we can factorize the u squared and v squared. This has become 1 minus cosine squared theta, which is equal to sine. So we get the result as sine squared theta. And we need to take observation that the sine squared, when we take the sine on the sine theta, we take only the positive sign because sine theta need to be a positive value, which means the theta is going to be from 0 to pi. All right. So that's the cross product. Okay, this application of the cross product, one application of it is to compute the area, okay, of the parallelogram. So if we have this parallelogram like this, it's described by two vectors u and v, and we know that this is v sine theta, the component. The area, okay, we can say the area of this parallelogram is the base, and the altitude, right, is this vector, the magnitude u, and then multiply with the component of this v sine theta. And of course, from the our proof before, that this is going to be the cross product. Okay. So the area of parallelogram So area of parallelogram is just the length of cross product. U cross V. Yeah. Yeah, that's it. That's it. The area of parallelogram. Now another application is to find the volume of the parallel pipe. This is the parallel pipe. Okay. So let's say we have a V, we have a U, the vector, and we have a W, and then we have the V cross W as this height, the blue line, okay, and then we have an angle over there. And from some application here that the volume is always the area multiplied with height. So the area itself is the area of the parallelogram. VW is the cross product, V cross the W, and then multiply with the component of the height with the theta. Then if we take this triangle, so this is U, okay, this is theta, so this part is the component of U with the theta, then it will be the magnitude U cosine theta, right? Okay, now we can write also in this application here, so we can say that the volume is U dot V cross W. Okay. So this U cosine theta is from the dot, right? From the dot product. So it says that remember that if we have U dot V, this equal to U V cosine theta, right? So if we have the V now is V cross W, then this will be also U dot V cross W, right? Okay, so that's why we have this. And then there are also another terms for this type of the parallel pipe. If the volume is zero, of the parallel pipe 0, which means that the U dot V cross W is 0, then the vectors, all the vectors U, V, and W, they are on the same plane, or we call the coplanar. So that's why we don't have volume if it's 0. Okay. So that's the applications of the cross product. Okay. Okay, so the last sections of this vectors is about the equation of line and planes. So let's start. So equations of lines and planes. So let's start to give you some illustrations. That is, if we have this, okay, so we have a 3-axis x, y, z, and we have a vector v that's going to be describing the movement from P0 to some P. Okay. Now if we try to describe each positions of this point, we can also describe this point with another vectors that we call vectors r0. That is vectors from the origin to the point P0. Okay, and then we could introduce a parameter t multiplied by the vector v, and when we move this to point B, we could also say that it is actually our vectors r0 plus this parameter. Okay, so we could write down that the vector r is, or we could say the r is so let me write completely. So line L is given by position vector of r, where the r is r0 plus d vector v. So we call this the vector equation of line. Okay, let's say we are going to write a vector v in terms of a, b, c. So this will be in three-dimension system, and let the r0 is positions at x0, y0, and z0. So it goes to be the vectors r0 is from the origin until the x0, y0, and z0. Okay, and then r is x, y, z. So we could write the x, y, z vectors as a vectors is x0, y0, z0 plus some parametric t multiplied with the vector abc. Okay, so we could imagine that if we maybe increase t, we change t, we could say that maybe we take t from here, take t here, take t here, and every time this segment's changing, the t also getting changed, right? So the segment will also getting larger. Okay. And then from here, we could describe the parametric equations for a line. So we could say that, as we say in this line here, the red line here, so the line that passed through a point, any point, and then parallel to the vector v. So v is, we say, the directions. Okay, so v is well, let me write here. It's in fact the direction. It's described by these parametric equations. Okay, where t is any real number. Okay, we say that t is our parameter. Okay, so let's start with the example. Okay. Find parametric equation for line that pass through point 5, -2, 3, and parallel to vector, let's say v. So this will be direction, right? Which means that this v is a, b, c. So we could start with the x, the x0, y0, and z0 is this, right? So this will be 5 plus 3t, right? We get this by taking it into this form. Okay, and then y is -2, -4t, and then z is 3 plus 2t, right? If you want to like taking into the picture, this will be the picture. Okay. So it says that this 5 minus 2 and 3 is our positions. The initial positions, and this 3, -4, and 2 is the direction. So this is the vector direction, right? Okay. Okay. Now let's see another example. Let's see another example. So find parametric equations for line that pass through and to -3, -7. Okay. Now we have two positions. So this is position 1, position 2. So let's say we are going to move from position 1 to position 2, which means that we are going to take the vector, let's say vector v, as the 2 minus 1. So 2 minus -1, -3, -2, -7, -6. So we are ends up with this 3, -5, -13. Okay. So we could, maybe if we want to draw and check how it goes, the directions, we could have this. Okay. So this will be the position. Okay. This is the first position, the second position, and this is our vector. Okay. That is stated that the vector is from position 1 here to position 2. Okay. Okay. Now, after we settle up with this line, the next sections will be about the plane. Okay, the plane. Let me put the picture. So imagine we have a plane like this, okay, in our 3-dimension system. So after we have the best way to understand this process is, first is we know that this is our vector positions, right? R0 and R. Okay. And we say that this is the movement from P0 to P. Okay. And we can say that this vector here is the subtraction from this vector minus this initial vectors, right? Which is this. Okay. And then imagine that there is another vector here that is orthogonal to the plane. Okay. Orthogonal to the plane. Well, you could imagine, if you have learned physics previously, in physics we have something called the normal vector, or the normal, okay, the normal line. So we call this the normal vector, okay, the normal. We say with the variable n. Okay. So this is called the normal vector. And then to make sure that the point is in the plane, we need to make sure that the point P is orthogonal to the vector P. So point P is orthogonal to n. Okay. So we need to satisfy the dot product that is orthogonal, that the vector n dot the r minus r0 vector, they need to be 0. Okay. So they need to satisfy. So the vectors need to be satisfied this equation. Okay. We call this part, okay, the vector equation of plane. Okay. So if we write the n as ABC and let the R0 is our initial position, and R is our goal, like that. Then the ABC dot the x minus x0, y minus y0, z minus z0 is going to be 0, okay? Which means that this is going to be stated that the R and R0, they are in the plane and they are orthogonal with the normal vectors. So the equation of a plane we could write as this. So after we multiply each component, this will be the results, right? Okay. Now if we have a questions like example, the plane has normal vector 4, -6, 3, and passes through point B, 3, -1, -2. Okay. The equation of plane will be, we could directly write 4 and then write x minus 3 and then minus 6, y plus 1 plus 3, z plus 2, right? So 4x minus 6y plus 3z, and the other constant is -12, -6 plus 6, so it's -12, or this is equal to 12, okay? So this will be the equation of the plane. Okay. And we could find the intercept, okay? We can find the intercept. For example, we need to find where the intercept of x, so we need to make y equals 0 and z equals 0, and we get that x is 3, and then when x is 0 and then z is 0, then y is -2, and then when x is 0, y is 0, then this will be z equal 4. So all these 3 points will be the intercept for the plane. So we could draw also the picture of the plane is this, okay? So in the x is this part, y is this, and z is this one, okay? So that's it. I think we finished all the concept for the vectors. So from the definitions, the dot product, the cross product, the lines and planes, okay? So I hope you can review this, and perhaps I will make some assignments for you, so just wait for that assignment. So yeah, I think this will be the end of the lecture for the class today, okay?